Hello everyone, we are going to be solving daily Leetcode problem given on 26th July 2025, that was Saturday. 3480, maximize some subarrays after removing one conflicting pair. So before starting this problem, we shall have a small motivational quote. No one saves us but ourselves. We alone must walk the path, while others may guide or support us. No one can live our lives for us. We must take responsibility for our own actions, choices, and destiny. The journey of self improvement, healing, and achievement is ours alone to walk. Ultimate, Ultimately, goals and success depends on our own courage, effort, and perseverance. Right. So we are the ones that are acting upon our goals. So if we are focused on our goals and purpose, we should we should take them up with courage, effort, and consistency. Then we will always be able to achieve our success and goals. So let's go through our problem statement. You are given an array you are given an integer n, which represents an array nums containing the numbers 1 to n in order. Additionally, you are given a 2D array conflicting pairs, where conflicting pairs of a of AB indicates AB from a conflicting pair. Remove exactly one element from conflicting pairs. Afterwards, count the number of non-empty subarrays of nums which do not contain both A and B for remaining conflicting pairs A, B. Return the maximum number of subarrays possible after removing exactly one conflicting pair. Okay, so let's understand this problem better. Let's go through this example 1. So let's say we are given with n which is equals to 4. These are the subarrays that can be formed with n is equals to 4, right? 1, 2, 3, 4, right? And removing exactly one conflicting pair means, let's say we remove 2 3 2 3. Now conflicting pair will contain 1 and 4, in this case, in this example 1. So there can be formed 9 subarrays in nums such that the conflicting pairs A and B values will not be existent. So these are the pairs 1, 2, 3, 4, and both 1 and 4 is never seen in any of these subarrays. So that's the whole expectancy, and this is the number that is expected. So we count here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the number of subarrays, right? So the problem is expecting maximum number of subarrays we can achieve after removing one element from conflicting pairs. So if we remove one element, this is the value. So we can uh, remove 1 4 also. If we remove 1 4, let's say the possible subarray pairs that can be formed out of 1 2 3 4 is 1 2 3 4, 1 2 2 3, 1 2 3, and 1 2 3 4. These are the possible subarray pairs, and here we can also form so 1 2. Let's say we do not, I will erase this here, and so here if you see we have 4 pairs, and uh, the values that do not contain 1 and 4, 3 3 4 and 1 4. So we need to exclude this pair, which will leave us with 4 plus 3 7 plus 2 9. Similarly, if we are excluding 2 3, then also we would be left with 9. So removal of either of these conflicting pairs will result us with a maximum subarrays of number 9, right? So that's the whole idea. But we are asked to return maximum subarray. Let's see if this example 2 has to give us anything more. So let's say we remove 1 and 2 from 1 2 1 2 3 1 2 3. So we will also be having combination of 2 3 3 4 4 5 and 1 5. So these are all the possible combinations also that can be done. So 2 5, we have not seen 3 5. So the combination of numbers that can be formed, or the total subarrays that can be formed here, would be n into n plus 1 by 2. So that's a formula that we need to understand. So with this number that we get as n, so 5 into 6 by 2, which would give us 15 pairs, right? So if we see here 1 2 3 4 5, let's see if we have 15 pairs. 1 2 3. So I guess you would be able to understand when I write this, but I would not be bloating this additionally. But yeah, I hope you understand this. So let's say we remove 1 and 2 from conflicting pairs. If we remove this one, so we would be left with uh, 12 is what the answer says, right? So we can also end up with these set of pairs: 2 3 4 and 3 4 5. These are all the possible pairs. So if we count all the possible pairs, 1 2 3 4 5 4 5 and 8 plus 3 11 11 plus 2, so there might be other two pairs that we can form here. I hope you get the picture of what we are also expecting. So 2 3 4 5. So this is another 5 pair. So we can form such subarrays, and the number of subarrays that we can form, the unique containing unique set of elements, will be 15. This is the formula that we need to come up with, and this is the crux of this problem that that this problem is going to revolve around. Okay, so with problem being understood, let me just write the approach that we will be taking to solve this problem with our intuition. Okay, so with the intuition or the example 2 that we had, we should understand that uh, the number of subarrays that can be formed, the total number of subarrays that can be formed with a given number of n is equals to n into n plus 1 by 2. So that's a thing that we should get to understand quick. N into n plus 1 by 2 is equals to total number of subarrays. So in order for us to understand how we come up with this formula right here, n into n plus 1 by 2. So let's take some example. Let's say we consider how n is. So for n we get only one valid subpair. So for n is equals to 2 we get 1 and 2. These are the two possible subpairs. And 1 comma 2, and these are the pairs, right? So let's use this formula and let's see if this really works. So 1 into 1 plus 1 by 2. So this is 1. So 2 into 2 plus 1 by 2, right? So this is giving us 3, but we are only having uh, 2 subpairs here, right? So uh, another subpair here would be 2, the number itself that we are considering. So similarly, if we are wanting to calculate for, let's say, n is equals to 3, we get to form 1, 2, 3, and also 1, 2, 2, 3, and 1, 2, 3. These are the possible subpairs. So it would be 6. So let's see how the formula performs. So this would be 6. So this formula is also giving 6, and our example also is giving 6. So now that we have understood, or now that we are good to derive the number of subpairs is equals to n into n plus 1 by 2 as the formula, let's go to the next steps. So this problem is at least asking us to remove the subpairs where the conflicting pairs array values doesn't come into picture. So we need to remove all the invalid subpairs from the total number of subpairs. So that's the problem asked, and we are also given with conflicting pair, which would reduce the total number of subpairs, right? So we consider a subpair being valid if there is no conflicting pairs values. Let's say, for example, let's consider this example only. N is equals to 5, 1, 2, 2, 5, 3, 5. Say if 1, 1, 2, 2, 5, and 3, 5. These are the conflicting set of subpairs. So for n is equals to 5, we would be seeing these set of pairs. So 1, 2, 3, 4, 5. I would try to write all the possible subpairs, and these two, excuse me if I miss any subpairs, right? 3, 4, 4, 5, 1, 5, 2, 5, and 3, 5. Okay, so let's see what the formula gives us. 5 into 6 by 2. So 15 pairs, right? So we already have 5 here, and 7, 12, and 1, 2, 3, 2, 3, 4, 3, 4, 5. So 12 plus 3, 15. And 1, 2, 3, 4, 2, 3, 4, 5, and 1, 2, 3, 4, 5. These are the subpairs, right? So if we consider all the subpairs, then we should be getting a value of 15, which would be the total number of valid subpairs. And once we remove the conflicting pairs, such as these that we are seeing here, then our total number of sub pairs should reduce to 12, right? So if we consider this one, if we remove this and consider this as our conflicting sub pair array, then we should end up with a total number of sub pairs uh, being 12. I believe one of these arrays will also be moved out, right? So that's the whole idea. I hope you understood what this problem is expecting. So now if we are needing to come up with an approach, so first step that I would think about would be to uh, sort and make the conflicting pairs array such that the a value is less than b value, and also sort this. So for this we can perform a normalization operation where we run a for loop on all of the elements in the conflicting pair, and we check each of the items in the conflicting pair. If the value of a is less than b, then we are good, else we swap these values just to keep it normalized, and then we can also sort this. So that's the first step. This would help us further down, where we can come up with an idea such that uh, we can have two boundaries, left and right boundary, and we can consider, let's say, if there are two boundaries corresponding to a and b, then we can find all the invalid subpairs, and from there we can, this would be a greedy type of solution where we are finding all uh, all subarrays that contain a range and also before b, right? So we get such subarrays and we filter them down and we remove them from the total subarray. Total subarray formula we know, and with the greedy approach we shall find uh, the invalid set of pairs for each conflicting pair. So we would have already removed one conflicting pair, and there would be few other conflicting pair items. For those conflicting pair items, we need to remove all the sub pairs which act as an invalid one to get the uh, total sum of, to return the sum of maximum sum is what we need to return, right? So I will look at the problem. What maximum subarrays after maximum subarrays, maximum sum of subarrays. Okay, so maximum sum of subarrays. This is the problem asked. So for our greedy approach, we are going to, the greedy approach that we are going to design would be such that we iterate through conflicting pairs, and here we calculate invalidated pairs for each conflicting pair, and we also calculate uh, the total number of elements that can be gained or and max gain using few additional parameters such as we for us to before even understanding how this greedy approach works, I will give you another thought process which can help us uh, approach this solution better. So let's say we are given with 1 2 n is equals to 5 and 2 5 3 5, right? So these are the three conflicting pairs. So with sorted values obviously, and also normalize such that a is less than b. And now let's say if we form uh, boundaries such as we segregate them based on the 2 and the 5, and let's say b0 b1 b2, and now we divide these into segments such that uh, there might be an invalid pair within this piece of segment. Let's considering these two uh, pairs. uh, we can say that uh, we can calculate a certain base value such that n plus 1 minus uh, we can calculate this such that conflicting pairs of 1, this would give us the base. And also we can set this boundary by saying base is equals to conflicting pair of I plus 1 of 1 minus conflicting pair of I of 1. So this would give us this boundary, and with this boundary being calculated, we can track two largest values such that a left boundary such that we can say a start value that is conflicting pair of a, and let's say we set this as a max value there max value, and we set it as max 1 and max 2 being the next lowest boundary. Next lowest boundary, we can calculate what are the valid subarrays such that uh, we can say max 1 minus max 2 into base. So this would be our formula. So we will break this formula down to much smaller grains, but once we have uh, let's say a formula for gain, we can also compute total occupied, which is equals to max 1 into base, right? So these are the two formulas that we need to come up with. I will explain how I am at least writing these formulas now. So with the intuition of this, where we said we are defining boundaries between the b1 and b2, we will also be having two set of left indexes limiting, that is 1 and 2. This will be called as max 1 and max 2, which we will be keeping track of as we iterate. So we will be keeping track of max 1, which is equals to start, and we shall have a condition, say if max 1. If there is max 1 that is greater than max 2, then we will do it this way. We shall be doing it such that start is greater than max 1. Then we will be setting it this way, and max 2 is equals to max 1. So with these two things, else we will be setting max 2 is equals to start if we are at the first conflicting pair, right? So we shall also be adding this piece of logic, but for us to still understand how we come up with these two parts, let us go over an example. Let's say there are two left boundaries, uh, 4 and a 2 from conflicting pair, and we say that there are three parts. So think about it this way. Let's say we are given with 1, 2, 3, 4, 5 numbers, and our base will be calculated such that it would be uh, n plus 1 minus conflicting pair of 1, I plus 1, and if n is less than m, n minus 1 is less than m, then we shall be recalculating base is equals to conflicting pair I plus 1 of 1 minus conflicting pair I into I into 1. So with the base being calculated, uh, we can calculate the total gain such that it would be, where was that formula that I had? So gain is equals to max 1 minus max 2. So uh, into base, right? This is if you uh, take a pause and think through how we are coming up even with the total valid pairs. You We said that we had this formula n into n plus 1 by 2. Similarly, this also lies in the same order where we have two left boundaries, 4 and 2. Max, this is max 1 and max 2. So this might be a little tricky one where we are saying between these two what are the total valid subpairs, and that's the part of the gain that we are doing. And once we have that, the second part which we had was with respect to total occupied. We were simply having to do it this way, where base, the max 1 into the base. So these these will eventually end up with the total final formula where valid pairs, valid subarrays minus total occupied minus gain. So this is the plus the gain. So this is the final formula that we are going to use after populating all the total occupied, which we are going to run through all the conflicting pairs and also the gain uh, with the boundaries being calculated of max 1 and max 2. I hope this logic is kind of clear with the intuition. I will go to the Leetcode editor and try solving this problem, and let's see how much of our solution approach that we have here translates, or you guys could you could understand through this, right? So I'll go to the Leetcode editor and start coding it up. I would start writing the logic for the greedy approach where we iterate through each conflicting pair, and from there I will also add in the normalized and the sorted, the piece of code blocks for normalizing and sorting the conflicting pairs, but I will start writing with the for loop which iterates through the conflicting pair 0, and this would, so m would be the length of conflicting pairs. I would, and also we might be needing max 1, which is equals to 0, and max 2 the leftmost boundary, the second leftmost boundary, and also a value for gain, which the max gain at each conflicting pair, and also total occupied. So these are all the set of constants that we need. So if there is a next conflicting pair, then we set the base value to, once we have the base value, we need to calculate the max gain and also the total occupied, which we are going to do it this way. If max 1, if the start value is greater than max 1, then we set max 1 is equals to start, and also max 2 is going to be the max 1. Initially at the first iteration it will be 0 as we are starting with the first conflicting pair, and gain will also be 0, right? And else if start is greater than max 2, then max 2 is equals to start. And we know the formulas for gain, which we are cumulatively going to add for all the conflicting pairs. If gain is greater than total occupied, if is greater than max gain, then we simply assign max gain to the gain value for the specific conflicting pair. And once we have this, we shall be so we can come up with the formula total minus total occupied plus gain will be the maximum subarrays after removing one conflicting pair for this problem. So that's the expectancy, and we know that total will be by 2, and we need to return total minus total occupied plus max gain. So this is all that we need, and we, as we discussed, we will be sorting the conflicting pairs just to make the greedy approach work smoother or as we planned. This would keep the conflicting subarray pairs normalized such that value of A is less than B, right? Zero, one, pair, one. Okay, this should solve our problem. Let me try submitting and let's see if this solution works. As you can see, the solution gets submitted. Time complexity of the solution would be m log n, as we have sorting which takes about m log n time, and space complexity would be O of n as the space complexity. And I hope you understood this solution. Please let me know in the comment section if you feel there is any piece of logic that you did not understand. I am hoping that you would understand these set of formulas just to compute the gain and the total occupied, and the rest of things would be purely intuitional. And such kind of problems in an real interview would obviously uh, be given with these formulas is what I am thinking as an hint from the examiner or the interviewer, right? So which would obviously help us code this up or solve this problem a lot more easier, right? So let me know in the comment section how you felt about this video and how much uh, of my explanations was really useful. Thank you.